Welcome again, everyone. It's another episode of Dan Does Data tonight. Back from last week. We're back from vacation. We're full-on operational mode. You might be wondering, what are we looking at all these pictures of leaves for? We were building a self-driving car. That was last week. This is new week. We're working on a new project. Project sponsored by GrowMobile and Nerd Farmer. They are interested in this crowd AI challenge and generally trying to predict what diseases a plant leaf may have, or if it is diseased at all. So, I've agreed to take a look at this, just kind of read in the data set, get a model started, just sort of a first pass kind of view. And that's what I intend to do. So if you go to crowdai.org challenges and Plant Village Disease Classification Challenge, you can check this out too. You'll decide for an account, and the official challenge is over, but the data is still there. And you can sort of compare and see how you're doing. I haven't looked at the leaderboard yet. I don't want to know yet. I don't want to poison my analysis. I have seen on GitHub there's a few people have posted their results. They built a cafe model that's big and lots and lots and lots and lots and lots and lots of layers. I'm sure it's not actually hideously number of layers. It just looks like that, just as the way the formatting is done in cafe here, with one line for every attribute. But yeah, that's going to be the idea. There are 38 classes of diseases. And we've got, I think, a few hundred images of each disease. So some might be more interesting than others. Some of these, by human eye, you can tell, yeah, that leaf looks unhealthy. That leaf looks unhealthy. This leaf, I don't know, to me that would look fine. Some of these look fine. One of the classes might be healthy, for all I know. I do not actually have a keen knowledge of that. But we've got labels, about 20,000 images of leaves across 38 classes. And the goal is to say, this is this disease or this is that disease for each leaf. Problems with this data set. These images are not all the same size. They look the same size here, but they're not. I think they were all taken with the same camera, with the same settings, giving 256 by something image size. So they all seem to have been scaled to 256 in one dimension. And just to make things simple, I'm going to take whatever the bigger dimension is, squish it down to the small dimension. And then I'm going to rescale to 224 because that's what a lot of popular image recognition models work at. So what have I done so far? I just started on this, 30 minutes ago or something. Let me walk you through what I've done so far, and then I'll start talking through what I'm doing then. And then I'll be doing it, and then we'll have done it. Then everything will be good. Okay, so I'm operating in IPython, of course, down on the right here. I got a Vim session open because that's what I like to use. On the left, I've got IPython 3. I've read in some data already. Not all of it. More importantly, I've allocated memory for all my data. So in theory, I should not run out of memory. In theory. We will see. It's about 40% of my memory to hold all this data on a desktop computer, so we'll see what happens. These are just some standard Python things that I like to have. The OS module for reading files, math when you need to do simple math, NumPy for dealing with arrays, glob to grab lots of files using a star, an asterisk, a wildcard, TQDM to get beautiful for loops and let me know how long I've got, and SciPy is what's going to be doing some of my image manipulation, opening the images and resizing them. Okay, all this stuff, this is stuff for Keras, which I don't know if you guys heard the news. Keras is going to be part of the official TensorFlow distribution. So you can already use TensorFlow underlying Keras, but now it's going to officially be part of it. I think my understanding is it's sort of like a fork of the main Keras project, or they're going to take it's a re-implementation of Keras with some TensorFlow backends. You'd have to check Twitter to get more information. But that's really cool. I thought that was neat. So we're going to be doing stuff, probably a convolutional neural network is the kind of approach that I'm envisioning here, just to try things anyway. I'm sure there's other stuff you could do as well. But just as a first pass, to read it in, to make some sense of it, that's what my plan is going to be. sklearn just gives us some better metrics. For example, if you want to compute the F1 score for precision versus recall on a classification problem, which is what this is, If you want to look at the confusion matrix, which is always really important for determining, oh hey, class 1 often gets confused for class 5. What do you know? I've imported PIL, the Python imaging library here, in case I need to draw more things on the library. I do not think I will actually need that. I might take that out. That's because I stole some of my code from my self-driving car stuff. And of course, I got matplotlib and I turned interactive plotting on because I like to plot things. Things are beautiful. All right, so if you download that data, it is a tar file, and in that tar file is a directory, CrowdAI, and it has 38 more directories. Inside each one of those directories is a whole bunch of JPEGs. Some kind of hash information, something that I assume this is what the actual disease name is, and like a picture identifier .jpg. So you get a whole bunch of those. You get, no, not 38, num data, about 22,000 data points. So that's not too shabby at all, just for getting started. So I untarred that in my current directory. I said it's CrowdAI, open that one. I know there's 38 classes, so I can recreate these class paths. So CrowdAI C _0, 1, 2, 3, 4, 5, 7, 8, 9, 10 through 37. So it's 0 up counting. It's important to not get mixed up about that. You could just glob to get these. You could say glob.glob of datadir plus /star, but you're going to notice this gives you a random order. And you'll say, fine, I'll sort it. And I know this because I did this. And of course, that gives you ASCII-betical sorting. So you get 0, 1, and then of course, what comes after 1? 10, because this starts with a 2, so that must be later. I didn't want to deal with that, so that's why I'm making the class names. I'm reconstructing them myself rather than reading them from the data. Okay. The first thing I did is I just want to grab one of these files. So I'll grab one of the classes, the first one. Give me all the image file names there. That's D0. D0, all these files. And that's in a Python list. And to read them in, you can use scipy.misc.imageRead. It can read JPEG files if you pass it the file name. So that's some path to a file. And I'm saying read it in RGB mode. So I did that. And now you've got this NumPy array. You say, what is I0 dot shape? And so you see it's got 388 by 256 by 3. So 3 color channels, and it's a 388 by 256 image. So then I decided, all right, well, let me do this for all the images in this class. And so I did that. Again, using scipy.misc.imageRead, just for all of them. And there's 270 in this class. So there's not many in this class. I guess that's, yeah, 270 over about 22K. Yeah, it's a little over 1% of the data, so it's a little underrepresented, but it's okay. And you can use plot.imageShow to actually plot one of these images. And now you can see it. And now you can see, okay, well, there's 256 this way, 3 that way. Yeah, this leaf has some spots on it, so it's diseased. And it's got whatever this spotting disease is. Maybe it's specks. And you can look at another one. Here's a different disease, a different leaf. Same disease, same kind of spots. And you can look at a later one. I don't know, look at 100. Same kind of story. So that's something interesting that's kind of occurring. You get this picture of the leaf, and you got the spots in these locations. I guess it tends to be towards the end of the leaf, maybe. Just as a human being looking at it, that's kind of what I'm looking at. So that's curious. Also note, these are not square images, so that's something I might want to deal with. These images, they might not even all be on the same. They show radically different perspectives sometimes, like this one. Like this is clearly shot at an angle. Like, what are we going to do about that? I don't know. We might just ignore that for now. We might not. We'll see. Just something to be aware of. These look like mostly the same kind of leaves, which is not surprising. I'd expect certain diseases target certain plants more than others. I guess this is the same disease too. I clearly have not trained my eyes well enough to detect that is the same disease. Same plant leaf. I really ought to know what kind of leaf this is, but oak? I don't know. Just, I once considered doing a simple leaf recognition project as a data set. Just like, what kind of leaf is this? Maybe I should do that for clouds. That would be a good thing. Okay, so we got to deal with this problem of these are all in different sizes. Actually, I didn't make that clear. This one is 256 by 256. This other one is 256 by like 380 by 340. So they're different sizes. It's not just that it has more rows and columns. If that was the only problem, I would say that's fine. I'll deal with it. I don't really care. But they're different sizes. So I need to get them all to be the same size if I want to really process these in a way that's convenient. So just to figure out how to do that, I'm only working with the first class at first. And I said, all right, give me all the sizes. So having read in all the data, you can just call .shape on it. For example, I0.shape. And that tells you how big it is. And it's got 3 here for, of course, the 3 color channels, the red, green, the blue. I don't really care about that. I know there's 3 of those. I'm not going to mess with that. So I said, just give me the first 2 dimensions of the shape, the size. And so now I have this array sizes. And I said, okay, well, plot me all the sizes, the x versus the y. And I noticed something really strange, and I was almost certain that I did something wrong at first. But then I realized, no, it's just one of the variables is always 256. That's just the way this data is. So I thought, all right, well, that suggests a certain solution to this problem. I can take the bigger dimension and just cut out the edges so that it equals 256, or it's squared up. So I wrote a little function to do this for me called new dims, this thing here. And all it does is you pass it in your dimensions. And it's 256, 380, just for an example. And so the 256 is the smaller dimension. It doesn't get modified. So we want to create, say, okay, start when we cut the image, grab the first row or whatever in this case through the last row. But the other dimension, it's bigger. We need to chop the top and bottom, sort of. So start at column 62 and go only through 318. So not the entire thing. So we're chopping off part of the image, the top and bottom. And the way you do that is you say, all right, what's the smaller dimension? I call that smaller with minimum. And then you want to subtract the current dimension, so in this case width, minus the smaller. If the width is the smaller dimension, this is 0. And then you start at 0. Likewise, whatever my minimum was, whatever I came in on the left, I need to come in on the right, or likewise top and bottom. If I want to do that equally in this case. You could get really fancy and try to figure out the right place in the image. Just for a first pass, though, I do not want to worry about that. You play the same game with the height. And then you spit out those 4 values, where you start on the width, where you end on the width, where you start on the height, where you end on the height. And then I computed all those for just the first class, just to get a sense. And so you'll notice one of these is always 0 to 56, because that's just the way that it is. And the other one is some number to some number bigger than 256. But this difference is always going to be 256. This difference will always equal this difference. So I could add an assert in there if I really wanted to be paranoid to make sure. Okay, and then I wanted to see then I needed to actually do some resizing. Just to get a sense of what's going on, really. So if I do scipy.misc.image resize, you can resize an image. And this looks really messy. Let me try to make this a little more parsable. So II is just the current image. That's the current image that I'm looking at in the first class. NN is the new revised dimensions of that image. So that's one of these one of these guys. It says, hey, grab only these slots. And all this business is saying is just grab those portions of the image. And I'm rescaling the whole thing to 224 by 224, down from 256 by 256 essentially, using a cubic interpolation, and I want the final color to be RGB. And we're just using the zip here to pair up the image itself with the revised dimensions. And then you get an image that looks like this. You might say, all right, well, that looks basically like the image you saw before. Yeah, it does. Plot.fig. Plot.figure. Make a new one. Let me show you what that looked like beforehand. Oh, well, that image is already saying. Well, so this just shows you a little bit of the cubic rescaling. So we've lost a little bit of resolution, is all that happened to this image. But if you want to look at image 0, you'll notice something a little more stark. This is the original image. We say plot.figure, plot.image show, I of p of 0. There we go. If I could spell figure, that would be really helpful. Yeah. So we cut off the top and bottom. We sort of zoomed in a little bit here. And you notice in this case, we cut off some of this like top disease point. So maybe you would have rather cut from the bottom. But this simplistic view, we don't have that knowledge. But we still have several points showing this disease. So we're not totally toast. And it's this 224 now. So it might look a little grainy because you're kind of zoomed in. The background's kind of grainy anyway, though. And I really hope that doesn't matter. We'll see. We are going to see. So that's sort of what I want to do. I want to do that to every single image. And then I want that in a NumPy array. So the question is, how much data do we have? So I just counted up what are all the files in this data set using a big glob and then taking the length of that list. And so that's this. That's where I got the 22,000 number. And then I want to make sure to pre-allocate some space for that. And the question is, can I really hold that much data? So num data times 224 times 224 times 3 color channels is that many pixels. And if I use a byte for each pixel in NumPy, then it's that many bytes. And so you say, okay, well, it's that many kilobytes, that many megabytes, that many gigabytes. Thereabouts. There's powers of 2 that are not exactly powers of 10. I'm choosing to ignore that. That's a rounding error at this scale. So about 3.3 gigabytes. So depending on your desktop, you might not be able to hold all that. So you need to be very careful. If I couldn't hold all of it, I could choose to resize to a smaller scale, like 128 by 128. I could choose to like only use one color channel. Like maybe I don't care about the green because the green's going to be the leaf and that doesn't really matter. Or I could just make it black and white. Something like that. So I pre-allocated some space. I found out that if you just do numpy.zeros, it doesn't actually allocate the space. You have to like put some memory in there. So I did numpy.random.random or numpy.random.randint of like 0, 256, just to represent things that I would put in there of whatever this stuff would look like. And you say dtype equals numpy.uintdate. And that actually allocates all the memory because it has to create all those numbers and store them there. So I've already done that. And that brings us to where we are right now. So that took 20 minutes just to go over that. Hopefully it doesn't take so long to go over everything. All right, so let's hop right into it. Let's now try to create the actual NumPy arrays full of all these images that we're gonna use and we're gonna make. And then we'll get to making a simple model. If we get to like 5 minutes left and we don't have, maybe 10 minutes left and we don't have all the data read in, I will probably just stop and I will just demonstrate how to make the model, and I might make the data offline or I might leave it at that. We'll see. Okay, so I've got this much data. I've got all my images already set up. So I want to say for class in, no, I don't want to call it, for C in classes. Because C classes is this thing. For I comma C in I don't want that. Zip. No, just enumerates. So I want to know which class number I'm in. I could figure that out from the string, but I don't have to think about it. That's just, ain't nobody got time for that. And I'll want my targets. I want my labels to be numpy.zeros. Zeros. These don't matter as much. It's just not that much space. Num data, comma num classes. dtype equals numpy dot float 16. There we go. Come on. If I could spell zeros, that would be really helpful. There we go. And now we've allocated some space for the labels. Not a big deal. Okay, we have our classes. For each class, we need to read in each file. I don't want to screw myself over, so files, right? Where did I do this upstairs? I gotta look at, like, where did I do this? I did it up there. So images. Equals glob of C plus slash star. There we go. No problem. So that'll give me the class. That'll give me a list of all the images that I need. And it's going to be a scipy.misc.imageRead of essentially IM. Whatever the current image is going to be, mode equals RGB. That's pretty straightforward. And then we will immediately, well, that'll be the image. Image temp is going to equal that. I'll say size S equals image temp dot shape, and we only want the first two things. Question from the audience: why am I streaming in 480 rather than HD? Because my internet is terrible, and if I was streaming in HD, I probably wouldn't be able to actually push any data through. And hopefully, and I'm not showing like a sweet video game where the high precision graphics really matter. I mean, it's a screen of text with the occasional graph and heat plot. So hopefully that doesn't make a big difference. If this is a little like small, the text, just let me know. I can fix that. If we want to reclaim a little, we can also reclaim a little screen real estate here. There we go. Now we should be at like 33 lines or something. About 30 lines, yeah. I found that that's pretty reasonable. But yeah, that is why I do not stream in HD. Also, that puts a lot of stress on my graphics card, and I need the graphics card to do the research. I'm caught in a bit of a catch-22. If I wanted to, I could use a virtual machine or something like that instead. Alright, so that's our shape. Our ND, our new dimensions. I don't need that old file anymore. New dims. And that's just yes. Okay, and then we need this. Doink. Oh my gosh. Alright, and this is going to be for J, comma, right there. I am in enumerate images. There we go. That's what I was missing. Image temp. Image temp. There we go. And where do I want to stuff this? This needs to go into all data of, oh boy, oh boy, oh boy. I just need to keep a counter around of where I'm at. So count equals 0. And at the end, we'll say count plus equals 1. There we go. So all data of current count, so it's just that particular data point, is going to equal this SciPy baloney. SciPy to image resize, image temp. It's not NN anymore, is it? It's N. Alright, we'll call it NN. That's fine. So we've got our shape. We do that. And I increment the count. I need to set my label as well. So I'll say labels. Is before the count. Labels of count of which class I'm on. I just set that equal to 1. That just says, hey, which guy is this? Not a problem. Okay. I think that might actually be all that we need to do. But let me just walk through it real slow like. Let me just run a little test here. That gives me some images. This is all the ones in the first class. Okay. Set j equal to 0. Did I not need j at all? I might not have needed j at all. Alright, well, we'll see. In fact, yeah. Probably don't need j. I am equals images of 0. There we go. I am. So we've got some image name. I will say, hey, image temp. That's my actual image. I will plot that image, show that image. It's probably going to be a familiar looking image. Yes, it's this tall leaf right here. Okay. Now that I've got that, I can just start banging this over there. So there's our size, we know that. There's our revised size, that's familiar, that makes sense. Now let's... Alright, so all images has some stuff in it. It does. But it's garbage right now. I filled it with garbage. I'm going to do plot that image show and it's going to look like garbage. Random garbage. You might think you see things there, you don't see anything there. You can force your brain to see whatever you want to see. Guaranteed. You want to see a sailboat? You can see a sailboat. So, I want to read this in and fix this. It's going to give me a count. See how that goes. That did not work as I wanted, I don't think. What? All images. Derp, derp, derp. Misspelled that. That's what I get. Might need to put something on that line. Hang on here. Yes, okay, so that didn't go in yet because I probably need this here. I did copy this from above, so this might be okay. There we go. Ah, there's our image. Stuffed into all images. So that's good news. And labels of 0 contains 1 in the first position because we're at class 0. No problem. Alright, anyway, definitely do not need this J. That is unnecessary. In that case, I'm going to let this run. Let this crank for a bit. And I really hope I do not crash my computer. So this is going pretty fine. Yeah, I can do, I don't know, 200 to 300 images a second I can process. So this will take maybe a couple minutes, provided my machine does not blow up in my face. And it shouldn't. Everything should be fine. And what I'm going to do is I am going to save this data. I am going to save all images. That's what this is called. Let me double check how I do this. Do I do it here? I don't. Oh well. I will have to just remember how this works. I believe it's a file name. So I'm just going to call this crop disease, then BZ. Crop disease image. Crop image. Crop image done in BZ. I'm just going to pass in all images, and I'm going to save a separate one for the targets. This is just a convenience for myself. Crop labels. Labels. Crop labels 1 hot. Because we've got all those extra zeros in there, I could put the actual integer for which one it's in, but we've chosen not to do that. Alright, so we just got a few more classes to parse through on the left here. And it looks like, yeah, somewhere between 150 and almost 300 images a second. For the bigger images, if they happen to be larger, obviously that'll take longer. This particular class is rather popular. That's interesting. I don't know why that is. Like, why is this 2100? Ding! Okay, perfect. Okay. numpy.savez_compressed. Because I want to save these off to an actual file just so I can use later. File args keywords. But I don't want to make a list of my arrays. Well, maybe I can get away with it. Actually, I probably can. Probably I can get away with it, right? Probably, you think so? Let's see what happens. Let's see if I destroy my computer right here. If the stream suddenly stops, well, I'm sorry. Images, labs. I apologize. I will restart the stream very shortly, if that is the case. Not broadcast array. Curse you. Save Z compressed. File args keywords. Save Z load. Do you have things that do not have examples? Just need to. This is terrible. Arrays to save to files. Oh, so don't do a list. Well, okay. So just do all the arrays. Let's try that. There we go. Okay, hopefully things are alright. I really hope this does not. Ooh, that's not a good sign. Not a good sign. The terminal's not opening. But I should be able to hold, in theory, a second copy of it. If it comes to that. Yeah, see that 45% memory? That's what I'm talking about. Them 3 gigs right there, yeah. So I was not expecting this to take take all this time to save these images, but that's okay. Okay, that only took 10 minutes to sort out, so that's good. Next, we'll be wanting to make ourselves a little model. While this is saving, we can start setting that up. So, in Keras, this is a pretty straightforward model. It's got one set of inputs, the images, and it's got essentially one set of outputs, the class probabilities for each one of these 38 different diseases, one of which might be healthy, I don't know. Because of that simplicity or straightforwardness, we can use this simple sequential model. We don't need a model with inputs coming in over here, inputs coming in over here, and outputs going that way, and outputs going that way, sort of like with the self-driving car. Nope, this is just sort of a linear progression. And that, oh, I bet this is slow in the file system. But you know what? I have an SSD. It shouldn't be that slow. That's irritating. Oh well. So you say model equals sequential. That sort of makes an empty model. You can start doing model.add. And the thing you want to do is probably some convolutional layers. So let's do that business. So I have a convolutional layer, but you need to worry about inputs. because the very first layer, Keras needs to know what the heck size of thing am I dealing with. So I am just going to double check. Obviously I don't do that here because this is not a sequential model, of course. Okay, let's go back to my old font classification project. VAR data? VAR data in? Is that it? Maybe that's it. Yes, this is it. There we go, input shape. There we go. We're gonna have. Oh, do we have to reshape this monster? That would be terrible. That would be terrible. We'll see about that. This might be awful. Okay, but control of the terminal is back, so that's a plus. Should be 3. What the heck did I do in the... Huh. I was a little surprised. Model. That's convolve. Yeah, 3. Well, that's odd. Do I do some wacky? I might have missed a resizing. Putting the color channel first step. That might have been. Yep. That's probably what I. Gotta transpose all them shapes. One of these days. One of these days, man. One of these days. Alright, but I have all the data. All images. I should just need it all data. Would have saved myself a lot of trouble. So if I do that, object does not appear to be 8-bit string path or object. Oh, not image read, image show. Excuse me. And I don't know. Let's look at 10,000, just for giggles. Here's another leaf. This leaf looks kind of healthy to me. I don't know. Maybe it's got some splotches that I'm having a hard time seeing. You never can be too sure. Just another leaf. Alright, there's another leaf. Okay, cool. We might get burned here, though. All images dot shit. Yeah. We need the color channel to be the first one. So I need all images dot transpose. Yes, remember how this works here. And it's the order of the new. So 0 goes in 0. What was in 3 goes here, and 1 then 2. And I need to save this off to all images. What was this? There's no attribute transpose. What? Could have sworn arrays has transpose, of course. Okay, good. That's just a simple reordering to do. It's just a matter of how it looks at the data. So really, I need to take care of that here. All images equals all images dot transpose of 0, 3, 1, 2. There we go. And then resave it. I'm not going to resave it right now. I will resave it later. Okay, convolutions then. So we'll have that. So this is the number of kernels, the number of sort of like low scale features you're looking for anywhere in the image at this point in the model. So we'll say to start with 8 just to have something. You will probably be wanting a lot more than that at the first layer. And this is how big of a window to look at a given time. So we're looking for little 5x5 features anywhere in the image, 5x5 pixels. And this is across all 3 color channels. So the 5x5 window by 3. So 75 pixels are sort of acting. We have 8 8 features, each one based on 75 pixels at a time. And I want the output shape to be the same as the input shape. You're going to take some weighted sum of those pixels, and then you're going to put it through this ReLU activation, which should be pretty familiar with anyone who does image recognition kind of stuff. It's sort of, if it's the weighted sum is less than 0, it's just 0. If it's greater than 0, it just is what it is. Sort of a simple, straightforward thing to do. And then we can do max pooling, 2 by 2. So we've computed all these little 8 different features at all these different positions. So look at adjacent positions, and we only slide by 1 pixel at a time, so there's plenty of overlap. And say, all right, well, in this little 2 by 2 window, this feature showed through 4 times. Which one is the best? Take that one, throw away the rest. So we cut our image size in half, which is nice. So we're going to do that, and what I'm going to do is, I want to do this, I don't know, I like 5 for some reason is like the number of convolutional layers that I have. That's just something that I enjoy. You know what, no, let's not do that. Let's not do that. Let's just start with 2. And then suppose that at this point you had found like all the different key features, but now they're still in this structural shape, so you want to flatten. I believe that's how that works? Yeah. So that takes all you've got some sort of new pseudo image at this point with 8 color channels, if you can imagine. So imagine you had a picture of your farm with all the soil. And so that's 3 color channels, plus you've got the moisture at every location, plus the temperature, plus the acidity. I need 2 more things here. Plus the, I don't know, magnesium content, plus the nitrogen content. So if you could have an 8-dimensional array, an array with 8 in that dimension slot in reality. In this case, that's not what that's representing. These are just sort of 8 intermediate features, the score for those features at that level. So you flatten removes all the structural nature of that, because at this point you say, all right, well, I've probably got my most interesting features, knowing that there's a lot of nitrogen and stuff in this area and that area. Now I care, or now I no longer care sort of where it is, just I know upper left blob, here's some stuff. Let's say 32. Here we're going to do a dense layer. So every single output of our convolutional layer is going to be we're going to compute 32 different things based on every single one of those. And you know what? I should do more convolutions, because otherwise this model is going to get crazy. Absolutely insane. So each time you do this 2 by 2 max pooling, the size gets cut in half. So now I'm doing 224, and I'm going to cut it in half 4 times. Right? So my result is going to be a 14 by 14 image. And then I'm going to say 14 times 14 times 32 things, so I'm going to have 6,000 parameters at the level where I'm going into this dense layer. Let me do another dense layer just for giggles. And then we will add a final layer. Oh, I need activations, right? That's important. Let's use ReLUs, just because we can. So this 32 is just to compute some intermediate feature of intermediate features of the features above. And the goal is to collect those into interesting things that might be difficult for humans to understand without a lot of study, but help discriminate between these different classes. And at the end, we've got dense with num classes, like that. And now we want an activation that says, hey, all of these values need to be between 0 and 1, and also the overall, they need to sum up to 1 because they're probabilities. So I need to compute 38 numbers, each between 0 and 1. And the sum of those needs to be 1 because it has to be in one of these classes. It can't be in some other mystery class. If it were, we would just add that class as a possibility, even if it's sort of a catch-all class that catches all the other classes. Okay, that's sort of a basic, very basic model that we've specified. I don't want input shape on all these other guys. That is not something I desire. So let me just do this. So this is just, I'm just making the same 8 kernel layer specification again and again. But there'll be different weights and they'll be handling different sizes of things because it will be cut in half each time. Also, this first one deals with 3 input channels. All these others have 8 input channels because there's 8 kernels in the previous layer. But you don't have to think about that in Keras. It's quite nice. Quite nice. Alright, so let's do that. Let's just do this one step at a time, see where I goofed up. Right. N rows equals 224, N cols equals 224. It's important to see what things you forget. Activation. RelU is built into Keras, so you do not have to think about that. And max pooling also built in. And these are things that you might recall, I have here is where I first imported them. Okay. That first layer, that first convolutional layer went fine, so let's do the next 4. And those seem to be fine. If you got the model, you can say model.summary. Take a look at it, what you got so far. And so you can see it's starting to add up. It tells you, oh yeah, you do a convolution, then you do activation, then you do pooling. And you can sort of see what's the size of things. And you down here at the end, 8 by 14 by 14. So it's 8 by 14 by 14. Ah, that's right. So it's 8 times 14 times 14 times 32. 50,000 parameters going from my flattening to my first dense layer. So that's going to be a lot of parameters, and that tends to be where the bulk of the parameters end up. Just because you've got so many things that you're suddenly trying to get everything to everything. We flatten yet? We did not flatten yet. So you do the flatten, and then you take a look at the summary again, and you get down to the end and you say, there's 1568, which is 8 times 14 times 14. And let's just wrap that up and look at the summary one last time. And yeah, there's that 50,000 odd parameters there. And you get a few in each more layer here. It's interesting that that's 1056 and that's 12. Oh, that's 38. That's right. That's why it's a little more. So, about 60,000 parameters left here. So that's just the specification for the model. We haven't trained anything yet. How do we train the model? Well, we give it the data to chew on. So I like to store my training history, a little thing like that, model.fit. And what you need to pass in, if I gotta remember this right, is the inputs followed by the outputs. So the inputs are all images, and the outputs are these labels, the one-hot encoded labels. I believe that's right. Forgot about compiling. Dang near forgot about compiling. So, there's a matter of how are you actually training your model. So stochastic gradient descent is sort of the standard, most basic thing to do here. Where you take a few data points, you look at them, you compare their what your model predicts for those versus what they actually are, and you say, aha, I was off by this much. I correct in this direction a little bit, and I'll be a little bit more correct. You correct all the weights, a little bit at least. We're using categorical cross entropy, which essentially we get credit for how close the probability of the correct result is to being 1, and 0 for all the others. If we had a situation where you had you could have multiple tags on a given image, you would run into you might not want to do this exactly, or you would have to label your things more carefully. You wouldn't want to be doing softmax because it could be more than one thing, so it's not going to add up to 1 anymore. But that's going to be fine. I will use stochastic gradient descent. That's fine. So you have to compile your model, which doesn't actually compile it yet. It doesn't get compiled until you try to use it. It compiles what grinds it down to the GPU level to make it really fast and precise. So and it's actually writing some CUDA code behind the scenes, or it's calling libraries to do that behind the scenes. What else do we need? There we go. It used to compile it, but it does not anymore. It's something that irritates me. And we'll say validation split. I don't want to validate right now because these things are all in order. Shuffle. The validation split. If you say, "Oh, hold back 10% of my data to validate," that happens before the data gets shuffled, which irritates the crap out of me because that means I have to shuffle the data myself if I want to validate the shuffling. It's not impossible. It's just an irritation, something I shouldn't have to deal with. So I think this is right. So we're going to look at 32 images at once while we're training for the stochastic gradient descent part. And number of epochs is how many times you're going to roll through the data. So we're going to do that once. Let's see if this blows up in my face. So the first time you do something with your model, it will take a long time for it to return. This isn't because it's actually training yet. It's about to. But this is now when it's actually compiling. So 50,000 parameters, got to settle that up, there it goes. Okay, so things that matter here. ETA, it says this is going to take about 1,000 seconds to return, so like 15 minutes. So this model will not be done training before the end of this episode, essentially. But the model is starting to do something. Also, you can see sort of live what is the current accuracy of the model. And you say, oh, it's about 5%. Well, given that there's about 38 classes here, a little better than 5% means we're doing it about twice as good as random guessing. Now then, I believe the winners of the AI contest were able to get about 95% accuracy. I believe that's good. Let's check out the leaderboard. Now let's check out the leaderboard. Most of this was just dealing with the data, deciding what compromises we have to make in order to get it to work at all. Oh, they're competing F1 scores too. That's right. That's a sudden drop off. Pretty good, 90s and then 3%. Interesting. That's just funny. Apparently I could have gotten on the leaderboard if I did something more than nothing. Oh well, that's quite all right. But these people spent a lot of time trying to figure it out, read in all the data. They probably didn't make the same compromises that I made in an hour to get the correct answer. And you can see this accuracy is starting to climb. Granted, we are not using validation data with this, so we don't know how general this model is going to be. And this is just literally the first model we threw out there, so we don't even expect it to necessarily be correct. But we were able to, in an hour, set up our environment, read in this data, resize, understand how the data is stored, start to resize all of it, stash all of it into a format that we can actually use, and then create at least a simple model and start training it and see that it's doing something more than nothing. Accuracy is improving. So I think that's pretty cool. I think this is the purpose of this show, of Dan Does Data, to be educational in this fashion. There's no way in an hour live on a desktop computer that you're going to be able to compete at the highest levels of one of these challenges. It just simply takes more time, more understanding, trying things that don't work. Training takes a lot of time. But getting up to speed on these kind of things, getting you to a point where you can say, all right, now I can just iterate, I can try real hard, lots of different things. And you don't have to worry about as much of the other data stuff. But that setup takes a lot of time. All right. I want to take any questions from anyone watching now, comments, anything. That's a good time for that. Model training is the best time for Q&A, I think. Oh, man. All right, that accuracy is improving. I'm going to guess that this can get at least 10% accuracy on a pass, one pass of the data. Just a guess. So, and once again, this was sponsored by GrowMobile and Nerd Farmer. So I want to thank them for sponsoring an episode of this. and they're donating money to a nonprofit for that. It's not going to me, but I still want to thank them for doing that. Question from the audience: do I do machine learning data science for a living? I would say I do data science for a living. I do some machine learning type stuff as well. I spend a lot of time not necessarily working on the neural networks, but working on low-level statistics, trying to define like the one true feature that will tell me what the answer is. And that's sort of classical science in a sense. Spend a lot of time dealing with dirty data sets. Spend a certain amount of time with soul-crushing bureaucracy. So that's where I'm at. I do this for a hobby. This is a good way to force myself to learn some of these tools, to interact with different data sets and understand what's going on, to meet people who are also interested in these kind of data sets. For me, that's what it's really been about. I've been doing this for a little over a year now, and I've learned a whole lot, and it's been fun. I get to do it live. There's no editing. If I make a mistake, I just get to fix it again. So it's very nice. Ugh. All right. I think that is probably going to be all we have tonight then. You're going to see this accuracy continue to climb. But, as always, I want to thank everyone else for coming out. One final question. What are your next steps to improve the model? So, I would try playing around with the number of convolutional layers and how many dense layers that I have here, just as the first thing I'm going to do. I would add a lot more features into these convolutional layers. So instead of 8, I don't know, try like 32, try 64. And as your image, the like two-dimensional size decreases because of this max pooling, increase the number of features that you're going to look at. You can rig it so you're going to have about the same number, but you don't necessarily have to do that. That might be the first thing to try, just to get familiar with it. Then the second thing I would do is look at what the winners did. And not steal, but learn from what they did. So you can see, he's got a whole bunch of convolutional layers doing all these things. I would re-implement this model in Keras. That's what I would do. Do I have videos for newbies? I have lots of videos for new people, especially if you're new to the tools. So if you go back in my old playlists, you can find my sort of more introductory videos. I have a series of videos on TensorFlow, people like that. I've got a series on Theano, people like that. I've got a series on Keras, people like those. I've looked at a couple other things. If you want a sense of a project from like start to finish, I would look at a project called For Well Thou Knowest. That is a project that it's a font classification problem that I came up with, that sort of shows you how convolutional neural networks can be used and be pretty useful. And it goes from, I might have started at creating the data, or at least parsing the data, building a simple model, building a slightly more complex model, a little more complex model, and finally ending with, what are some crazy things you could try to do here? All right. That is all I got tonight. So once again, I want to thank everybody for coming out. And I want to thank GrowMobile again for sponsoring this episode. And don't forget to stay safe in the data mines. Take it easy.